In this lab, we will try to use our microcontroller in low energy analog comparator mode. So in our lecture, we studied about analog to digital analog comparator, and there's this low energy sense peripheral with the main idea that the CPU is sleeping, but there's some mechanism which automatically samples the comparator, and then only if the comparator value is between some thresholds, only then the MCU is woken up and some action is taken. However, I will also show you, how we can use Silicon Labs examples so that we don't need to write from scratch. The previous labs we wrote basically from empty page, which is good. We need to train our brain and improve our game, but we can also use the example projects as the starting point of our project. So here we will click in the launcher view, new project. We will create a new project. Then we have some example projects for our starter kits. And one of them is lightsense. And let's read the explanation. Lightsense, or example using low energy sense. So basically this demo, what it does is it samples the light sense using comparator, not ADC, and does some action. So let's use this as the basis of our project. And in real life, when you create some gadget, some electronic device, you would usually find an already existing example project, which is the most similar to your application. And then you create a new project with that, and then just add some features that you have. So lightsense example, let's click on that in new project, example project. Next, let's leave the default name, link SDK and copy project sources. Next, and finish. Okay, so in this project explorer, in the left side of the screen, are visible all of the projects that we have. On your regular project, right click and click close project, because when you compile, all open projects are recompiled. It takes some time and you don't need that. So let's have all other projects closed and only this SDK lightsense project open. And let's check out. There is lightsense configuration file in which we can change some configurations. Initially, we'll just use the default configuration, and lightsense.c file, which has the code. I would like to point out that a good style is to name the file in which the main code is located as main.c. So in this file, we have function main. This is the entry point into this project, into this application. So the file that contains main should also be called main.c. It's a good convention because let's say you change your job, you move to a new company, and the previous company hires a new programmer. When the programmer opens this project, they have to find where this main code is. And if the files are named like libraries and drivers, and there's no main.c, this poor person doesn't know where the main entry point is. So this file should be renamed lightsense, instead of lightsense.c, to main.c. So for now, let's see if we can do it. You right click on lightsense.c, click rename, and call it main.c. Okay, now let's try to build this file. Let's hope that it works. Okay, so it compiled, it's 18 kilobytes big, and let's just flash it and let's see how it works. Flash to device, program. So this file, also we can just walk through this example project. to understand how it works. So we go to this main code, which is in line 355 in our main.c newly renamed file. And there's this chip in it. Obviously, there's something called core declare IRQ state. I don't know what that is. There's board support package trace profiler setup. It's just for some debugging, but BSP is board support package. So when you create the board, if you make it as similar as possible to development kit's board, then you can also use this BSP. Otherwise, you would not use it. But generally, this thing initializes clock management unit. And if we control click on it, we can see how the clocks are initialized. So first of all, high frequency source is high frequency RCO. LFA source is low frequency RCO. And LFB is disabled to save power. What is this system core clock update? System core clock gate. I don't know what it is. It probably checks out which clock we're using in our project. So if we look at in our reference manual to the clock management unit, basically what this code does is it initializes the low frequency domain A to work from low frequency RCO, and core to work from high frequency RCO, which is on by default anyway, and low frequency domain B is switched off entirely because this project doesn't use low energy UART 1 and 0, so nothing new. Then we enable high frequency peripheral clock. Actually, I think it's turned on automatically if you don't do this. And this project will also use low LCD, analog comparator number 0, peripheral reflex system, core low energy, pulse counter 0, real-time counter, low energy sense, and also it sets a low energy sense prescaler. And basically it turns on all the clocks. Now we need to go back to main. Now, then it initializes the GPIO. So basically initialize GPIO lightsense excite port and sensor port. And in this example, it shows one thing. If you use a pin as an input, you can set its mode to disabled. It disables the buffer, so the pin consumes a little bit less energy. And we can do it in our project as well. Then it also initializes the button 0 and enables an interrupt on falling edge and enables IRQ for interrupts. This is a pretty massive code. It also initializes comparator. And, you know, if you spend some time reading this, it's easy to understand. There's this initialization structure, and it's just initialized, and some levels are set for high and low level. Then there's peripheral reflex system, which basically says that you can connect a low energy sense to channel number 0. And pulse counter, which counts pulses between two events. And there's also this low energy sense, which has some pretty complicated configuration, but once you set it up, it basically works on its own. And the real-time counter, which has an interrupt, something like every 1 second, right? Okay, yeah. And also there is a segment LCD driver. And now what this thing does is basically it checks the buttons. If you press the button, then something happens, LCD turns on and shows you some information. And now let's look at our development kit. So when the light is, when the light suddenly changes, this thing shows you the light level. And then after some time, it switches off. I think it's after 3 seconds. And now let's press the buttons. Button 1 shows this information. And button 2 doesn't do anything. But now let's go to Energy Profiler and check out how much energy this project consumes. So as you can see, low energy sense samples the analog comparator's input, and both of these things are built in such a way that if the comparator input doesn't change, if the light is approximately constant, then basically it consumes almost no energy. But if this light level suddenly changes, let's see, then this low energy thing wakes the CPU up and outputs the message on the screen. The reset. So I changed the light sensor level. 1 second. Okay, and it's off. So in this example, we can see that analog comparator and low energy sense consume almost no energy. And LCD actually also consumes very little energy. This is why LCD is still used actually. It consumes only something like 4 microamps. It was displaying the text, but it only consumed this little energy. And the only time when the CPU consumed lots of energy was when it woke up and output the message on the screen. And then when only the LCD shows the picture, it sleeps again and only consumes 5.96 microamps. And when the time of real-time counter expires and you need to switch off the picture of the LCD, then it wakes up, switches off LCD, and goes back to sleep. And in sleep mode, it consumes 1.56 microamps. So it's a very, very low energy application, which is, very good for battery saving and so on. So again, I also press the button. And as you can see, when I pressed the button, the consumption was a little bit higher. When I released the button, it was lower. But again, a good example how the processor can use almost no energy and actually be working in the background. Okay, so I'll end session now. So if you have to build a similar application, for example, if you need to, instead of light, you need to sample, for example, button presses, you can use this code and just modify a little bit. And instead of a comparator being connected to light, you can connect it to a button or some other analog signal. But basically, you can use Silicon Labs example project, and just add some lines of your code and use this thing, and it will consume very small amount of energy. So basically what I want you to do is just create this example project, go through it, check out that it compiles and it flashes and works, check out its energy consumption, and basically that's it. We're not gonna edit this, but you just have to know how to use it. Okay, so that's all for this lab.